We return now to our study of the position going around a unit circle. That defines through derivative the velocity function. At any point we can determine what direction our instantaneous velocity is going in and at what rate. And we can also compute the acceleration by simply taking one more derivative. So we take the derivative with respect to time of r prime. That's going to give us r double prime of t, or something we might call the acceleration vector. And again, we just have to do this component by component. We take the x component and take the derivative. We're going to get negative cos of t. And we take the y component and we're going to get negative sine of t. And that is the acceleration at any t. We can reinforce that a little bit by picking a particular instant and illustrate with a of 0. And that's going to be negative cos of 0, that's negative 1, and sine of 0, 0, so that's going to be 0. Let's put those ingredients together on the diagram here briefly. We have our velocity vector, and remember, velocity is where we would end up if there were no acceleration acting on us. But we do have an acceleration, and that acceleration is actually pointing inwards, directly towards the center, as it turns out. And that is going to cause a bend, the velocity, because it represents the change in velocity. So if our velocity is this, but we apply this acceleration to the left, we're going to end up pulling that velocity leftwards. And we know that that's going to result in a few seconds later, or fractions of a second later, a velocity that's still pointing upwards, but a little bit to the left as a result of that acceleration. Now there's some nice ideas about projecting vectors and whether this results in a change in speed. This acceleration is perpendicular to the velocity, so it turns out there's no way for it to add speed, but it does change direction. And that gets us into some interesting developments about our intuition about the relationship between position, velocity, and acceleration, which don't show up until you get into vector type problems like this. So take a moment to consider this question here. Which statement is true about the acceleration for this orbiting dot using the same formula we had a moment ago? Take a moment to consider, and then we'll investigate. The acceleration vector is constant. Well, that's pretty clearly not true, simply because we have a formula for the acceleration, and we can tell that if we sub in different values for t, we're going to get different values of the acceleration vector. What we can see, though, is that the magnitude of the acceleration is constant. If we look at the magnitude of this, no matter what t value we sub in, we're always going to have cos squared and sine squared values, and so we're always going to have a magnitude of acceleration of 1. So think about that as the strength of the force that would be applied to the moving object, but the direction will change. In fact, we saw that in the last slide. We would have an acceleration that points towards the center initially, but if we picked any other time point, it would also point towards the center as well. In fact, there's a nice simple relationship there. If our position is defined by cos of t and sine of t, then we found earlier that r double prime was going to be negative cos of t, negative sine of t, and that is exactly the negative of the position vector. Let's slide in some t's here. And so if our position vector measured from the origin is r, then the acceleration vector is just a negative of that version of position. So if that's our position, then this will be our acceleration. There's a number of ways to interpret that. The one I think that's most important for us is that the acceleration is always towards the center of the circle. And as another consequence, because this is circular motion and our acceleration is equal just to the negative of the position is always 1 unit length away from the center. So the acceleration is always constant, always 1 unit in length as well, constant in magnitude. Again, just a quick reminder that the directions of the vectors are probably the most important to compare here, but remember the units are different. Our position is in meters, while our acceleration is in meters per second squared. So while the directions are comparable on a diagram like this, it's not that easy to compare their magnitudes because they're in different units.